Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Good afternoon. Welcome to MIT's Faculty Forum Online. I'm Robbie Stewart, a PhD student in Course 22, Nuclear Science and Engineering, and I will serve as our moderator today. This broadcast is sponsored in part by the MIT Federal Credit Union and MIT Professional Education. Closed captioning is available. Click closed captioning below. Joe's pointing that out in the chat. A reminder that after we hear from today's guest, we will field questions for him. So please use the Q&A feature on the Zoom toolbar to ask your questions. And we'll get to as many as we can in the time allotted. Today we're hearing from Professor Arig Danagulian, Associate Professor of Nuclear Science and Engineering at MIT. Professor Danagulian's research interests include nuclear nonproliferation, technologies for treaty verification, nuclear safeguards, and cargo security. We'll post a link to his full bio in the chat now. Today, we're excited to hear about his new research on simpler, more cost-effective, effective nuclear warhead verification. Welcome, Professor Danagulian.
All right, thank you, Rob, for the great introduction. Hello, everyone. It's great to be here, even if online. So I'm going to share my screen, and I'm going to start with the talk. All right. Hello again. So we're going to talk about specifically the problem of the large nuclear arsenals and what scientists engineers can work on as a way of reducing the threat associated with these enormous arsenals that we have. So we're going to cover lots of things today. Just very generally, we'll talk first about the policy aspects of this problem. What's the current state of affairs with the nuclear arsenals? What is nuclear arms control? How do we do verification of arms control treaties and how we do not do that? We'll talk about information. We'll talk about physical cryptography, the concept of physical cryptography and zero knowledge. Then we'll talk about the physics that we use as a way of achieving the goals. Okay, specifically about nuclear resonances, nuclear structure, as well as nuclear experimental physics that contains physical cryptography in it. And finally, then we'll talk about engineering. So we'll talk about compact verification devices. So we have about something like 30 to 40 minutes, and we're going to cover 4 quite distinct topics. So hold on to your seats, and if this feels like drinking, this sounds like having to drink from a fire hydrant, that's exactly what it is. I hope it will make the alumni nostalgic about their days as students at MIT. So let's start off with the discussion of what is the current situation as far as nuclear arsenals are concerned. This is a plot from the website of the Arms Control Association. These are the nuclear stockpiles and arsenals for the 9 known nuclear weapon states. You can see that essentially 90% of the weapons are in the hands of the Americans and the Russians. And something I want you to pay attention to is not just the total number of weapons, which is in order of 6,000 each, right? But the number of the deployed warheads. Okay, so deployed warheads in this shaded area. And what does deployed mean? Deployed means a warhead that is ready to be used. It has a delivery system associated with it, which could be a ballistic missile. It could be a bomber aircraft. In principle, it could be like an artillery unit, which we don't use anymore. But these are the ones that are essentially sort of field usable, so to speak. And there was a New START treaty was signed about 10 years ago. They set a ceiling of about 1,500 warheads. And the American and Russian declared arsenals are below that number. Now, this is a fairly large arsenals, nevertheless, right? So 2 things going from there is, one of them is these arsenals are kind of a lot smaller. This is still quite terrifying. Okay, 15,000 warheads. That is still, depending on how you use it, that still could be used to exterminate significant fraction of the world population. Okay, but these numbers are quite a bit lower than what they used to be. During the Cold War in the 80s, the total number of warheads was like around 70,000 warheads. And we're now down to 15. So that's a significant progress. So the question is, how did we come down from 70,000 to 15,000? The short answer is because we're signed arms control treaties. And the question is, well, a treaty is not only as good as its verification system, because if there is no way to verify a treaty, then then the two sides don't trust each other, and they are just not gonna. They either will cheat or simply will not abide to the treaty, or simply will not sign the treaty. And to just express this conundrum, Ronald Reagan in the 80s, he liked to impress Mikhail Gorbachev with little Russian kind of sayings that he would learn, and one of his favorite ones is this "доверяй, но проверяй," which means trust but verify. The question is, how do we do this verification? And before talking about verification, the other thing I want to talk about is, you see this difference between deployed and total, right? And essentially we have these deployed warheads, which is order of 1,300 or so. And then we have, on top of that, we have another 5,000 warheads that constitute the stockpile of the retired arsenal. Okay, and essentially in the past, the treaties primarily focused on the deployed warheads. They didn't really focus on the stockpile. Okay, but the stockpile can be just as dangerous in some situations. So this is like, I'm trying to separate the stockpile from the deployed arsenals. Okay, now it's kind of very tempting to think of arms control as a purely political process. If only people get together, they agree, they will. No, there's quite a bit of evidence from the past that lack of a technological verification or lack of technological means to verification has essentially torpedoed quite ambitious and very useful treaties. Essentially, the most kind of clear one, the most obvious one, was a comprehensive test ban treaty. The comprehensive test ban treaty was essentially signed and eventually ratified by most countries in the early 90s, but it was first floated in late 50s. Okay, in the late 50s, okay, Eisenhower was interested in passing a comprehensive, complete, absolute ban on testing. Okay, and why did it not happen? Well, to understand why it did not happen, Glenn Seaborg, okay, the famous chemist, has this very nice book called Kennedy, Khrushchev and the Test Ban, where he really goes over the events that led to the failure to pass a CTBT in the late 50s, early 60s. And he essentially really describes that one of the main problems that prevented the passage of this treaty back in the days was a lack of forensic seismology, or lack of a precision of forensic seismology, in that seismology in those days could not really tell the difference, okay, between a 20 kiloton nuclear explosion and the equivalently powered earthquake. These days, they would easily be able to do that. But in those days, they couldn't do that, okay? And in those days, there were many people who were hoping that using forensic seismology would be able to achieve verification, and because we can do verification, we can have CTBT. That didn't work out because there was multiple other issues that came up, also mostly technical issues. Edward Teller, the famous Edward Teller, who was the inspiring character for the Dr. Strangelove, he essentially he goaded Rand Corporation and others to really do this analysis, which showed that there's other things that Soviets theoretically could do to prevent the detection of tests and things like that. Long story short, because we didn't have the technology back in the days, that essentially was the main, at least according to Glenn Seaborg, was the main thing that sabotaged the CTBT. And instead of CTBT, they passed the limited test ban, which only banned testing above ground and in the water, while testing below ground was not forbidden, and it went on, and that became the basis of further expansion of nuclear arsenals. 40 years of an arms race, multiple close calls that could have ended up in accidental nuclear war, all that stuff. Perhaps had the technology been ready in the 50s, the world would have been quite a bit of a different place, would not have had this terrifying close calls that we have had. So, okay, so how did people do kind of verification? So we discussed about forensic seismology, which is now what is being used among other methods to verify CTBT, comprehensive test ban treaty. Okay, but when it comes to specifically reduction of the arsenals, okay, where no explosion is happening, okay, most of the verification was done, has been historically done by eyeball, visually, okay? So first of all, nobody has really verified the dismantlement, the disposition, and the liquidation of the nuclear warheads themselves. Instead, most of the verification has focused on the delivery systems themselves. Again, delivery systems means something that delivers your weapon to the target, okay? And focusing on delivery vehicles is not such a bad idea if you are looking at this purely from a point of view of a nuclear war scenarios, of achieving strategic balance, making sure that two sides have similar strike capability. And the reason is being because your strike capability is ultimately limited by the number of your delivery systems. Okay, if you have 1 million warheads and only 1,000 missiles, all that counts are the first 1,000 warheads. Okay. So that's not such a bad thing to do if all you care about is intentional nuclear war. Okay, so how did people do it? For example, after the INF Treaty, the Soviets and the Americans agreed to dismantle all their intermediate range nuclear weapons. That meant essentially convincing to each other that delivery systems associated with them have been dismantled. So this is a Soviet operative looking at a Griffon cruise missile, American Griffon cruise missile, which is the nuclear, I think, version of the Tomahawk missile. This is Senator Lugar in Russia staring at the Yenisei class intercontinental ballistic missile before it's carted off for destruction. And essentially they look, they say, yes, this is a real ballistic missile. It's not something made out of papier-mâché. And then they also, with their eyeballs, they can see that it's being transported somewhere and cut in pieces or something like that. And most dramatically, as part of START Treaty in the early 90s, Americans agreed to dismantle 365 of their B-52 strategic bomber aircraft. They took them out to this desert in Arizona. There's a graveyard for airplanes. They used these large guillotines to chop them in pieces, which effectively totaled the aircraft, destroyed the aircraft irreparably, and had essentially the Russian satellites flew overhead, took pictures. The Russians eyeballed the pictures, said, yes, okay, this clearly they destroyed them. So when it comes to strategic balance and things like that, this visual verification may be sufficient because we're talking about very large systems, okay, that are difficult to fake, okay. But if you want to focus on other problems, the problem with this is that this leaves out these large stockpiles of nuclear warheads, the surplus, if you will, of nuclear weapons and nuclear devices, very clearly. Specifically, the problem with them is that they could be stolen, it could lead to nuclear terrorism, unauthorized nuclear use. The two countries could maybe actually transfer it to their allies. So there's a risk of nuclear proliferation. So for the future, we hope that there will be treaties that will specifically go after the nuclear weapons, the nuclear devices themselves, okay? And in order to sort of verify, in order for two sides to verify that they are dismantling actual nuclear weapons, there needs to be a way to authenticate these warheads before dismantlement, okay? So question is, authenticating an ICBM, because it's so large, it's not so difficult. But what does a weapon look like? Okay, so this is a picture of the so-called reentry bus of the Peacekeeper, now has been is defunct, which is armed with up to 13 what are called reentry vehicles. These reentry vehicles are these like black cones, okay, that are about my height, about 180 centimeter tall or so. Okay, and this thing contained the nuclear explosive, the bottom of themselves. Essentially, these are the things that you shoot your ballistic missile out of the atmosphere, it goes complete open space, goes up to an apogee about 1,000 kilometers, and then these reentry vehicles have to re-enter the atmosphere. So verifying that this thing is a real weapon is very difficult. Okay, in principle, these sites could just open them up and show their contents to each other, but that would be out of question. Like, Russians would never allow Americans to put their eyes on the actual nuclear weapon and see the structure of the nuclear weapon, let alone a third party, for example, the multilateral treaty, and vice versa. Americans would not want the Russians to find out technical details about the weapon. Okay. So there seems to be kind of a paradox, how to verify that something is a weapon without letting anyone look at it. So we believe we have a way of dealing with this problem. Essentially, we need to have something that is both accurate in terms of accurate in that it can detect hoaxes and clear, honest objects, and is secure at the same time. It essentially achieves privacy, does not reveal anything more than, yes, it's a hoax, or no, yes, it's a hoax, no, it's not a hoax, it's a real weapon. So people in the past I'm sort of skipping lots of interesting details. People have been working on this problem. It's not a new problem, has been around for quite a long time. You could, for example, acquire some data from the weapon that in of itself could be highly classified, but there could be software encryption, okay, that says, yes, it's a real weapon. But then now problem is that, well, the software can be hacked. And you in principle can achieve the same encryption in in analog electronics or digital electronics. But again, the electronics, people have proposed the so-called electronic barriers, information barriers. But again, those things could be hacked as well. And we believe that this process can be achieved through physics processes, where essentially your measurement process intrinsically, okay, protects the information. You measure something that is fundamentally has the information already encrypted in it, okay? And that can only give you yes or no answers, nothing more. The reason the previous two, as tempting as they are problematic is because effectively you are shifting the burden of verification from the weapon, okay, to these devices, to the electronics, to the software, okay? And both electronic software have components that, there are millions of components, okay? They're actually more complex than the weapon itself. So if anything, you have made your verification challenge even harder if you have to now verify the information barrier. With physics, okay, you cannot hack physics. So at that point, rather having someone trust you, rather than having the 3D partner trust you, you're asking them to trust their understanding of physics. Okay, and hopefully that's a much lower barrier of entry for kind of negotiations. All right, so how do we approach this this problem? The way we approach this, and there's multiple different paradigms for looking at this, is there's something called attribute verification, and the one we focus on is template verification. So the general notion is that the inspection team, okay, gets hold of something that we will call a golden copy, okay, which is essentially a warhead, a particular warhead that is authentic. And I'll say in a second how do you get something. But you get hold of one warhead that is golden and you hold on to it, okay? Then you take this warhead and you go to, say, some kind of a bunker or some facility where there is warheads that are have to undergo dismantlement, and they're of the same design as your golden copy. And now what you're doing a comparison, right? And looking inside the warheads, you're comparing them to each other. You're asking, is A0 equal to A1? Is A0 equal to A2? Is A0 equal to A3? Are they identical? If A0 is authentic, and if the A0, A1, A0, A2, A0, A3 are all identical, that makes A1, A2, A3, A4, AN authentic as well, okay? At that point, you send them to dismantlement, and you count those dismantled warheads towards that country's obligation under the treaty. Now, what is the sign of equal? How do we put sign of equal between black boxes? Okay, that still we need to answer that. But to understand the general characteristics of the comparison, okay, there's two things that need to be guaranteed. One of them is that you need to protect secrets. Okay, you need to achieve privacy. Okay, so for that you need physical cryptography, and we'll talk about physical cryptography. And second one, identity. Okay, identity ideally means that at the same geometric position in 3 dimensions, you have the same isotopes. Okay, so I use the word isotope. Isotopes are important because uranium-235 and uranium-238 are not the same things. It's not sufficient to verify the same elements. They really have to be the same isotopes. So you need to have some kind of a physical measurement process that is sensitive to isotopes. And the nuclear resonances, if you can measure them, are a great way to tag an isotope and to differentiate two isotopes from each other. Okay. So I mentioned this golden copy, just kind of, operationally, how to get hold of that golden copy, because everything hinges on that. The general notion is that IAEA, International Atomic Energy Agency, has done this many times. This is part of their general approach. You do unannounced visit to an ICBM site. You pick the site randomly. Then you come to an ICBM and you randomly pick an ICBM, okay? And you open the nose cone of the ICBM, and you randomly pick one warhead. In order for the country to have a nuclear deterrence, it needs to have real weapons on their real ICBM. So by picking one of these warheads, okay, you essentially have made, you're certain that warhead needs to be authentic. Okay, Russians could try to put fakes on the day of the inspection, but it means that on that day they will not have nuclear deterrence. That's an extremely high risk, because if they were to be attacked, they would not be able to retaliate. All right, just to give credit to many other people who have worked before us. Lots of work has been done in the national labs. Okay, work has been done also with our colleagues at Princeton, okay, at Sandia, Berkeley, University of Michigan. Many people have been working on this problem. Generally, I would separate things into two parts. There's like template verification, attribute verification. information barriers of physical cryptography. We argue that combination of template verification and physical cryptography, okay, essentially is the strongest way of solving this problem. The color code here is active versus passive methods. Essentially, Princeton and MIT are following active methods, who are very active people. And there is a very nice paper by our colleagues from Princeton who sort of survey the field. Okay, so I talked about this isotopic sensitivity and the need for measuring resonances as a way of getting to this thing. So there's a number of nuclear processes, okay, that you can measure that will tell you that what isotope you are dealing with. One of them is nuclear resonant fluorescence, of which I will not talk about today because we're extremely limited in time, but this was one of the earlier ideas that we had. The idea is that if you shine, high energy photons, or actually intermediate energy photons, at the nucleus, then with some luck, if it's the correct photon of the correct energy, you will have a transition to some nuclear level, okay? And from there, you will have decays. And when you have decays, new photons will be emitted. If you have a very high precision detector, you can detect those gammas or photons, and their position, their energy will tell you which isotope it is. So here's an example sample of a spectrum in MEV. These are the resonances from uranium-238. This big one is actually from aluminum. Just to think about the resonances, okay, just think about atomic fluorescence. Okay, if you don't have background nuclear physics. So this is like emission spectrum from hydrogen, okay? If you heat up hydrogen, if you hit it with electrons or photons for that matter, you can get the hydrogen to be excited from its ground state to first, second, third excited state. And then when it decays back down, it emits an optical photon that you can measure and quantify using your grating spectroscopy or something like that. And similarly, or just if you have hydrogen gas, if you shoot white light through your hydrogen gas, then what will happen is that the photons of the correct wavelength will undergo absorption and reabsorption, the re-emission, okay, into the 4 pi, which means they are very unlikely to get to your eye. And you will see what is called an absorption spectrum. So the same lines will be missing in white light that traverses hydrogen gas. So this method is what we use to look at some kind of some object, glowing object in the outer space and see what it's made out of by looking at these lines that that object is emitting. Similarly, we can look at light coming from a faraway star, and we can see which lines are missing, and that will sort of tell us what is the interstellar medium made out of between us and that star. But basically, think about like these resonances. Every time you have a bound system, you're going to have resonances. Whether that bound system is an atom, whether it's a nucleus, whether it's a proton or a neutron. Proton, neutron also have resonances for people from high energy, intermediate energy physics. Whether it's a guitar string, they all have resonances, okay, the moment you bind things. And that's essentially it. All that's different is the energy necessary to excite that those resonances, which depends on the binding energy, of course. This paper was published a while ago, but the basic principles are the same in what I'll be talking about, which are neutron-induced resonances. What I talked about before that was photon-induced resonances. Here we're going to talk about neutron-induced resonances. So you can kick up nuclei to their excited state using many different probes. You can use photons, you can use neutrons, you can use protons, you can use muons. Okay, neutrons are great for a variety of reasons, but the general idea is that if you have got a nucleus, okay, this is like a picture of a xenon nucleus that I'm sorry, not xenon, radon nucleus that I found online. So you have got a neutron coming in of a particular energy. This nucleus has specific resonances too, okay, which means it specifically resonates with probes particular energies. If the neutron is off resonance, okay, meaning its energy doesn't correspond to right thing, it just bounces right off of this ball of a nucleus, okay? And essentially the probability of this interaction, this is called hard sphere or potential scattering. The probability of the interaction essentially depends on the size of the nucleus, roughly. That's all. It's really sitting there like a little dummy, like like a ball, like a cannonball. You bounce off of it. Probability of hitting it just its area very roughly. However, it's not really cannonball. It can vibrate. It can oscillate in different things. So it is very dynamic, very sort of kind of if you're vibrant, if you will, system. If the neutron's energy happens to be equal to the energy of the resonances, what will happen is the neutron gets absorbed into the nucleus. And after that, you get this sort of, you go like on the isotopic table, you go to one isotope over, with one extra neutron. And then if it's short-lived nucleus, then what happens is two things can happen. One of them is that it can shoot the neutron right back out, okay? Or it can decay to a ground state, depending which energy level you have access to, okay? This interaction is typically described very well by Bright-Wigner formalism. And this is the spectrum, this is a cross-section of the, depends on cross-section on energy for a number of plutonium resonances. So you see this very sharp resonances. I mean, this is log scale, so some of them go all the way to like 10 kilobarns, 20 kilobarns, okay? While the potential scattering, which is the bottom, is just a few barns, maybe tens of barns at most, okay? So you can really see that resonances are truly, truly resonances, okay? Now, here's an interesting thing that you might ask. You notice the energy scale, it's electron volts. You might ask, on Earth can an electron volt neutron access a mega electron volt nuclear level? And the reason being is this reaction over here has a Q value, which is non-zero. It's actually MEVs, okay? That Q value combined with this extremely low energy of the neutron, okay, essentially gives it like a leg up, okay? Allowing an EV neutron to access an MEV level, okay? This is the level scheme roughly for two nuclei. So essentially what happens is that if the neutron happens to have just the right energy to hit one of these resonances over here, it will be captured, okay, it will be absorbed, and then you'll have these decays that will emit gammas. Okay, this is one of the fascinating things about the neutrons, that an EV neutron can do this. Okay, so this was all physics, okay? Now we're gonna talk about, let me just verify Q&A, there's any questions? Okay, so I'll, just a clarification, I'll try to answer most questions during the Q&A. If there's a clarifying question, then please specify it as a clarifying question, and Robbie will interrupt me and ask me to clarify things. Okay. So how do we use this? Oopsie. Yeah, there we go. How do we use this to verify warheads? Okay, this is great. We know that we can do isotopic measurements. Okay, isotopic measurements are a great way to go from a measurement space to isotope space. Okay. Not every measurement spaces will map to isotope space. If you measure the mass of your warhead, that is not anything specific of its isotopes. That's not a one-to-one map. But this is measuring these resonances is a map to isotope space. So how do we do this? So imagine you have an object and you shoot neutrons through it. Okay, and this is actual data from Los Alamos, where our colleagues from Los Alamos measured transmission. This is the energy, again, electron volts, and you can see these absorption lines. Okay, neutrons have been lost because of a particular isotope that absorbed them at a very specific energy. So this happened to be the absorption lines from uranium-238. So you know that the object contains uranium-238. And from the depth of these lines, you can know the amount of material that's in the way. So the spectrum tells you which isotope it is and how much there is there. Okay, this sounds like a great idea, except there's a problem. If you were to do this on the real warhead, you will learn everything about it. You will learn the amount of mass that's in the way. You might be able to learn its geometry and all that stuff. And remember, that is not allowed. Just doing simple measurements like this is not allowed. Okay, the treaty partners will simply not sign a treaty that says that you're going to come and do this to their weapons. Okay, so there's an additional step yet you have to do. Remember, I mentioned the physical cryptography. Okay, to achieve physical cryptography, you need to add an additional layer. You need to add what we call an encrypting mask or encrypting filter. Okay, the notion being is that the hosts provide the object that's going to undergo dismantlement. Typically, we think of a weapon component like the plutonium pit. Okay, for those who are not familiar with like weapon speak, pit is the plutonium fuel or uranium fuel of the weapon itself. Okay, and that's probably the most critical part of the weapon. So the idea is that the hosts provide both the component, and they also build this encrypting mask. They build encrypting mask. The inspectors don't know what encrypting mask is made out of. And the idea is that if you're doing a measurement, now you get a spectrum, but that spectrum, okay, depends on what the pit is made out of and what the encrypting mask is made out of. Because you don't know what encrypting mask is made out of, you cannot uniquely determine the content of the pit itself. It's a one equation with two unknowns. So you do a measurement, you get a spectrum. This is an actual spectrum that we took the lab with tungsten instead of plutonium. We don't have plutonium at MIT, at least not in large amounts. And so you do measurement with your golden copy. Then what you do, you replace the golden copy, okay, with the candidate device. Okay, so you know that this spectrum comes from an authentic warhead with an encrypting mask, and you cannot figure out what the warhead is because there's this encrypting mask in a way that you don't know what it is made out of. So then what you do is you swap your golden copy with a candidate object that you're actually trying to verify, and you get a second spectrum. And you ask yourself, are the two spectra identical? If the two spectra are identical, and if the encrypting mask was kept in place, which inspectors can verify visually, make sure nobody moved it around, then that means that the two objects that you measured are probably identical to each other. There's more nuance to it that I'm not going into, but nevertheless, this is essentially the gist of it. Okay. Just to sort of give it another way, to look at this another way is, remember I mentioned like one equation, two unknowns. So you first do your first measurement. You have got your encrypting mask, which is Y, you got your golden copy X, and you measurement, and all you can do is measure and say the sum of them is equal to 10. 10 units, doesn't matter what. Plus minus some uncertainty, right? And then what you do is that you replace your golden copy with a candidate weapon and you do a second measurement, okay? You find out a number that is very close to 10. What can you learn from this system of equations? You can learn from system equation because Y was identical. You can, if you subtract it from each other, you can find out that X prime must be equal to X within the uncertainties and things like that. At the same time, because this is two equations and three unknowns, you cannot find out what X and X prime are. At most, you can put an upper bound. Knowing that Y is a 0 or positive number, okay, that is a natural number, you can at most say that X is somewhere between 0 and 10. And Y can be made large such that this upper bound is large enough where this 0 to 10 is useless information. For example, you can set up your measurements such that they find out that the amount of plutonium in the warhead is between 0 and 10 kilograms. That's entirely useless information because we know that, of course, the mass of plutonium cannot be more than 6 kilograms. So, you know, yes, the upper bound can be made useless entirely. Okay. All right. So essentially, this is where we achieve verification using this thing, and this is how we achieve privacy. Okay. Okay, so how about actual measurements themselves? So we can essentially, the way we have done some of our measurements is we don't have plutonium, we don't have weapons. Instead of that, we have used molybdenum tungsten. Molybdenum tungsten have similar properties to uranium and plutonium, at least as far as resonances are concerned. So if something worked with them, it must work with plutonium. I'll skip a little bit. The idea is that we have essentially a neutron beam, which we operate in time of flight configuration. It's a pulse, big neutron pulse. Neutrons arrive to the detector. You detect the neutrons. You measure the time of flight. And from there, you can calculate the velocity and the energy of the neutrons. You put your essentially object that you're trying to verify. You have an encrypting filter in the way, and you measure this spectra. Okay. And in the experiments that so what does a spectrum look like? Here's an example of spectrum very briefly. This big absorption lines correspond to tungsten, and these thin absorption lines correspond to molybdenum. We can see both of them. So we had a two set of measurements. One of them is we wanted to verify that if you change the isotopics of the object, you will see the difference. So we built objects, cylindrical objects. Okay, one of them was molybdenum tungsten. And first we tried this what's called an isotopic hoax, where we just shift the isotope ratios around. Less molybdenum, more tungsten, and we see can we see the difference between those, right? If we cannot see it, then forget it. We cannot do anything. And then we worried about geometric hoaxes. Remember, this is a 0-dimensional measurement that ultimately also has to give you 3-dimensional information about the geometry. Isotopics is not enough. You also have to verify the geometries are correct. So the way we approach this is we did build a geometric hoax, which looks identical along the z-axis, but is very different along xy axis. Okay, it's a cube. And in order to compare them to each other, we will do rotations, okay? So the idea is that you compare two objects along one axis, and then you take some random rotations, and you do comparison under some random rotations as a way of verifying that also geometrically they are the same, okay? So first thing first, we check our isotopic hoaxes. We switch between 90-10 ratio, okay, 90%, 10% ratio to 50-50 ratio. And the spectra, they look completely different, right? We go to the other extreme, we switch 90-10 to 10-90, and just like even by eyeball, you can tell that the spectra are very different. We don't rely on eyeball. unlike the ICP-M measurements. We do a simple chi-square test, and the chi-square test tells us that the probability that these two spectra are identical is 0% down to like 6 decimal places. Okay, so no question that this is a hoax. We can tell the hoax from the honest object, and then we go to the next scenario, which is we compare the genuine object, the honest object, to the cube, which is a geometric hoax. And look at that, the spectra are identical. Well, of course they're identical. We built the cube to be identical along z-axis, and we're doing measurements along z-axis. It would be surprising if they were not identical, but remember, we're going to do rotations. So first measurement is along 0 degrees. Next, we do measurement at 45 degrees and 90 degrees. And here the spectra differ. Spectrals are not so big that you can see by eye. But our chi-square test, as simple as it is nevertheless extremely sharp. It can see what you cannot see by eyeball, and they can tell you that probability that are identical is nevertheless 0 to something like 3-4 decimal places. And again, you use this as a way of rejecting this, and you say that clearly these are hoaxes. These are geometric hoaxes. Okay, and again, we chose 45, 90 degrees because just because it happened to be the easy way of doing this. But in real measurement, you would take just random angles, okay, to prevent some kind of optimization of the geometric hoax. Finally, we do the last thing, which is we go one step further and we ask ourselves, what if all these discrepancies that we saw before were because of system fluctuation, because the accelerator wasn't working right? How do we know that it was happening because of the physics of the process and the physics of the geometry and the isotopic things like that? How we are sure that that's what it is? So what we did was that we used this object and we did multiple measurements at very different times. We actually shut off the accelerator. We had access, the beam trip. We get it working again. We did another measurement, and now we do comparisons along 0 degrees, 45 degrees, 90 degrees. And we find out that throughout all of them, we have essentially complete perfect match, okay, better than like something like 50% agreement that the spectra are identical. So no, the fact that we saw discrepancies before was not because of system fluctuations. It was because of the of intrinsic properties of the object themselves. So just to summarize, we were able to reject isotopic hoaxes, we were able to reject geometric hoaxes, and we're able to confirm honest candidates. And let's see, I have maybe 5-10 more minutes, so I'll go a little bit faster. So far, I've not said anything about information security. Let's see, we have some questions coming up. Okay, and so remember, I said that we need to show that all you can infer is an upper bound, right? So what you want to show is that your signal is only sensitive to the sum of your object and the encrypting filter, okay? And that's not the way we approach this problem. Essentially, it is the following. If you're doing a measurement, you want to show that it's just the sum of object plus the mask, okay? So you want to show is that these 4 scenarios that I drew over here, you cannot tell the difference between them. If you can show that your signal for these 4 scenarios or 3 scenarios or something between the 2 extremes are the same, then it tells you that the inspector cannot tell the difference between this object and this object. And that essentially is what I was saying earlier, that at most I can infer an upper bound. So what we do is we do these measurements. We actually run simulations at this point. We took the data from the experiments and we run simulations where we had configurations where we had one scenario, there was no pit, just like air instead of it, and a very thick filter, and then a really, really thick pit and a very thin filter, and then something in between. And we show that their spectra are essentially identical. If you run the chi-square test on this, you find out that they are essentially identical. If the signals are identical, it means you cannot tell the difference between these 3 scenarios, and that tells you, but what's common between them is that it's the same combined area, like I said earlier. And that tells you that the inspector cannot distinguish between no pit being there and a really, really thick pit being there. So thick that is larger than the critical mass. Okay, so they learn nothing by looking at this spectra. You can do the same thing with isotopics. I'm going to skip a little bit, but essentially you can really show that there's no useful information comes out of these measurements other than the 2 objects are identical to each other. So this is a measurement technique that is very sensitive to differences and very insensitive to absolute values. That's what you need for this. We published this work about a year and a half ago. You're welcome to go and read up about this. And in the last 5 minutes, I'm going to talk about an additional problem, like engineering-wise, where we are essentially, so far, the experiments where the facilities where you can do these measurements are limited to fairly large user facilities. Okay, this is the facility at Los Alamos. I took a picture from a screenshot from Google Maps. I mean, this is a kilometer-long facility. Okay, and Gartner Lab, where we actually do some of our experiments at the Rensselaer Polytechnic Institute, okay, is about 400 meters long. Again, it's a huge facility. Could you do some of your verification, inspection verifications there? You could build a facility along the lines of what the Gartner Lab has, but it's a fairly difficult thing. Okay, it's for logistic reasons, for practical reasons, it's going to be very difficult things. And the reason these facilities are so big is not because you really need them to be big. They were built to be big because they are supposed to produce these extremely precise beams. Okay, but the question is, do we really need extremely precise beam for what we're doing? And the answer is probably not. Okay, so the question is, can we use smaller neutron sources to achieve what we're doing? If we can, that will allow us to go from this mesoscale, I call them mesoscale, it's a pun to mesoscale, and also because the facility occupies a whole mesa. This is the North Mesa in Los Alamos. Can we go from this mesoscale to something much smaller? Just few image pictures of what people, by the way, have used these techniques also in many fields such as archaeology, material analysis, for imaging, isotopic imaging. It's quite exciting. So it's a very powerful technique that is extremely encumbered by these huge facilities, okay, that are not very accessible. It requires beam time access, whatnot. So what we did is that instead we said, okay, let's see if we can do this with a simple DT generator. DT generator is a little device that's about the size of this table or even smaller. Instead of costing $1 billion to build the facilities, it costs only about $80,000. Okay, most physics departments and Department of Nuclear Engineering have them. Okay, and we decided to make a measurement at the distance of approximately 2 meters instead of hundreds of meters, things like that. And ask ourselves, can we pull this off? The answer is, of course we can, otherwise I wouldn't be talking about it. But the idea is that we take the DT generator, we put a moderator around it that slows down neutrons, makes some of them epithermal, and these epithermal neutrons, EV neutrons, go through the material, get detected, and you look at their spectra from time-of-flight data. You also get significant backgrounds. So I'm going to skip a little bit more, but here, let's just go to the one plot. Here we go. So this a little bit of a busy plot is what you can see is this is the not energy, but this is a time of flight, which is the reciprocal of the energy. Okay, longer time of flights mean lower energy, shorter time of flights means higher energy. This is roughly the range between 1 EV and something like 200 EV. Okay, electron volts. So this line over here is our, actually what I want to do is so this line over here, okay, this plot over here is the open beam where we have nothing. It's just the neutrons coming through. And then what we do is we put a number of materials. We put indium, tungsten, etc. And this is the spectrum that we get. Okay, I need to delete the previous slide. So you can immediately see that there is this absorption lines, big, thick absorption lines. That this one corresponds to indium. This one corresponds to tungsten 182. This corresponds to tungsten 183. Different isotopes, same element, different isotopes. This is for silver. There's a big, huge resonances from tungsten 186. There's a cadmium here, and there's other tungsten isotopes. As we go to shorter times, our energy resolution becomes worse. But at this range, at least we can are very clearly differentiate different lines from different isotopes. Okay. Just very briefly also, we can also measure transmission. And the black over here is the transmission data. The blue is a cross-section that is causing this. So you can see that the cross-section is going up, the data is dropping down. As you would expect here, the cross-section is going up, that absorbs the neutrons, and we get this dip. And the black line is a fit that essentially uses a background model and uses cross-sections to calculate the expected transmission. And this is for a number of different elements, silver, tungsten, indium, and uranium-238. And we essentially have a fairly good agreement, about 10% deviations, which we think is probably because of our either background model or because our open beam data was not the right one. But basically it shows that this technique could work. We could actually get away by using fairly small devices. We don't need those massive devices. And if this, this could allow you measurements at a very small scale. Okay, so this would really help do the future treaty verification inspections. Again, why we're doing this, because we want to go from a kilometer to meter size, from a $1 billion facility to $100,000 instrument. And I'm joking that we want to go from mesoscale to table scale. Of course, all those who know Spanish know that mesa means a table. All right, these are conclusions. We have shown that we can use a photon and neutron probes to do this work. We have shown that we can use a small DT generator to do this. There's many applications to this in archaeology, in materials analysis, pure enrichment analysis. We're actively collaborating with the national laboratories. We have a beginning of a collaboration with the South Koreans. Okay, and we hope to also collaborate with the Russians through National Academy of Sciences joint US-Russia project on monitoring and verification. Generally speaking, our goal is to develop technological solutions for big societal problems. And of course, the problem of the nuclear weapons is probably one of the biggest ones. And with that, I'm ready for your questions. I'm going to leave you with a picture of men and women who have made this work possible. I believe this is most of them. All right, and I'm ready for questions. Sorry.
Great, thank you so much, Professor Daniglian. I'll just remind everyone real quick to ask your questions using the Q&A function in the Zoom toolbar, and then you can also upvote questions inside there if someone else is asking something similar or something you're interested in. That helps us prioritize them. So our first question is actually a clarifying question I missed, but from I think your first slide on the total warhead counts, do MIRVs count as multiple warheads in the first chart you showed and in the tree?
So I'm not sure what is the terminology, the semantics of exactly a warhead. Typically, a warhead implies you have an ICBM. It has one head, so it has one warhead, and then the warhead might have multiple devices inside, right? So I guess MIRVs essentially they're part of the way I understand the terminology, the semantics of it, is that the MIRVs, plural, they make up the warhead.
Got it. Thanks. All right, our second question here from Mark. We were very worried about losing 0.2% of people that get COVID in 2 years, and having also many long haulers, perhaps lifelong. But nuclear weapons can kill billions of people and ruin the planet for decades and hours to days, and can be unleashed by any leader of US or Russia. Shouldn't the world now be focused with verification on getting rid of all of the nukes worldwide, such as 5% per year, so that the world is much safer for all 20 years?
The short answer is, of course, right? There's no question. As you very aptly pointed out, questions are disappearing for some reason. Open, answered. Yep. Oh, I see, because there's open and answered ones. Yes. Let me just keep reading this. Yes, absolutely. I mean, as you said very, very clearly, stated very clearly, why are we ignoring a problem that can kill hundreds of millions in hours and possibly 1 billion from starvation over months? It does not mean we should abandon all the COVID-19 ill. Obviously, there is a real worry that since the end of the Cold War, sort of this problem has been sort of swept under the rug and people have sort of forgotten. Also, I have a sense that, as the problems become bigger, psychologically, human beings just stop thinking about that because they just cannot internalize the scale of the catastrophe, of the disaster, of civilization-ending event is so large that it's almost like humans just sort of, it's a one cop-out, there's some kind of a cop-out way of just saying, oh, it's just never gonna happen. Just let's stop thinking. Because if you think about it, you may go insane. So I am thinking about it all the time. I do not go insane. I do realize the scale of what it can do to my society and to my children. I don't go insane because I'm working on this problem that gives me a sense of agency and sense that I'm doing something towards this problem with the hope that it will make a dent in this problem. But yes, I think we do need to sort of raise awareness in the newer generation about the danger and the fact that this danger hasn't gone away. The notion that it would be crazy for the Russians, for North Koreans, for the Americans, for that matter, we're not that exceptional, to start a nuclear war. No, okay, yes, it's crazy, but what if we have a crazy leader? Or what if we do have a rational leader? Okay, but what if there's an accident? What if there is a miscommunication? We have this so-called, launch on warning posture, where essentially, if we see an attack or we think there's an attack from Russia, the president has 5 minutes to make a decision that will end 1 billion lives. Okay, and the president has to make that decision within 5 minutes. And what if that decision is made wrong? What if too late we find out that it was some kind of a flock of birds in front of the radars, or some kind of light bouncing off of cloud, as it has happened in the past? These are very specific close calls that we have had, or some other problems, or what is so there is in fact quite a bit of, now it's not having weapons and no weapons, right? There's intermediate steps we can do. For example, we can work on de-alerting our ground-based deterrent. We can maybe move our ground-based deterrent to submarines, okay? This whole launch and warning is coming from the fact that, from this so-called use them or lose them mentality associated with the ground-based deterrent. But if you can move the ground-based deterrent, I'm talking about the ICBMs, to the submarines, okay, to submarine launch ballistic missile configuration, then, and these submarines are extremely well protected, both by water and by their invisibility, unlike the ground-based one, whose positions are extremely well known. Then now, instead of having 30, then the whole use them or lose them goes away. At that point, president can take his or her sweet time and make a decision. At that point, you have possibly a day to make a decision. So the risk of an accidental nuclear war goes down by orders of magnitude. Okay, so there's many problems, both from going to global zero, reducing nuclear arsenals, at the same time just rethinking, because lots of the ways in which we're thinking about nuclear deterrence is still from Cold War era. Many of these approaches have not changed in 35 years, okay? And that's extremely troubling. So let's see, next question.
Yeah, so next question from Sam Brady. What kind of technical and or strategic dimensions create the biggest exposure to cheating and running around your verification methods?
I assume this is a question about the incentives, why a country might be incentivized to cheat, rather than what are the technical limitations of the instrument itself. So when it comes to cheating, the notion is that why would a country try to cheat in general, right? So if they can really get away with cheating, you could imagine the scenarios where, like, currently we have something like 1,300 warheads, and let's say we have this really, I'm being very optimistic, a treaty that says that we'll bring it down to like just 100 weapons, right? In that, let's see, something happened. My screen sharing, I think, ended, but that's fine. So in that scenario, let's say, imagine that we have brought down, we believe the Russians, so let's say we have brought down our arsenal down to 100, and then we found out that Russians have been cheating all along, and they have 1,300 warheads. So that could essentially completely destabilize things. On, let's say, Russian side, or possibly if we have treaty with China, or America, also US side, might also be incentivized to play tricks like that. If you don't, this is I believe it's in a scenario where you have no barriers to cheating whatsoever. So if you do have barriers to cheating, then there's a general sense that even if there's a limited probability of being caught, the country would not risk the diplomatic crisis that will ensue to save a couple of warheads or something like that. Okay. Okay. Open questions. Next, go ahead.
Yeah.
Robbie.
Let's. I'm gonna jump to this one. Great work. Are international collaborations in this research hampered by research nationalities?
So it depends what you mean by research nationalities. We have people of non-US nationality in the US working on a number of problems. One of our collaborators, one of our colleagues from Princeton is French. I believe now he's actually he's working in France currently. So this is a problem that I know that both in the 90s, we used to have quite good collaboration with the Russians in the good old days when Americans and Russians were actually behaving like adults. That all fell apart in the 2000s for a variety of reasons, and it completely fell apart after the Russian invasion of Crimea. There has been quite good collaboration with atomic weapons establishment in Great Britain. I know that folks at the AWE are also working on this. The South Koreans are now interested in working on this, and I have heard that there is some interest by the Chinese to also focus on this kind of problems. So it's a very good question in the sense that collaboration between the nation labs and weapons labs between US and other countries is difficult. But academia is not limited by classification limitations. We're private citizens essentially, especially in a private university. So that in a way gives us this opportunity in academia to do this, if you will, track 2 development, where we do not need a clearance from the US government to go and talk to anyone, including the Russians. Whether the Russians will be interested in talking to us, that's a whole different question, because academia in Russia is not as free from state influence as the academia in the United States is free of state influence in this country.
I'm going to just give a warning that we might run a little bit past the hour, but I think Professor Dunaglin's indicated that that's okay, just so we can get to the rest of the questions here. I'm going to go to this one from Frank Camelio. Could the approach work by analyzing the decay spectra of warheads rather than using beam activation?
So yes, so there are a number of, remember that one of the first slides I showed, there was a couple of other methodologies proposed by the nation lab, by Oak Ridge, by Brookhaven, and by Los Alamos. I believe there's a TRIS is one of them. I forget what, but that essentially are doing that. They are measuring the gamma spectra from the plutonium and from uranium. Those could be used to passive. It's so-called passive signatures, that you're not activating anything. The downside of those is that they really don't give you geometric information. You could essentially, a box that has plutonium in it is not a weapon. Okay, warhead verification is a lot more than plutonium verification. Just to understand why, is Russia and the United States have a surplus of weapons-grade plutonium that is measured in tens of tons. We have literally don't know what to do with that plutonium. So if someone gives you a box and says, "Here, this is a weapon," like, no, the fact that there is a plutonium, just the fact that there's plutonium inside doesn't make it a weapon. Okay, it has to be a plutonium object of a very specific geometry. Okay, yeah. So yeah, those are interesting things, and in some situations don't want to dismiss them altogether, because in some situations, for political and practical reasons, perhaps maybe something that is not very rigorous might be accepted as well. So they are worthy, and they are worthy techniques.
So this next one has been upvoted from Andrew, and it's a little bit tangential. So what is your opinion, or do you have an opinion on breeder reactors to reprocess spent nuclear fuel as opposed to dry cask storage?
I do have an opinion, but I will not give it because I'm not a reactor engineer. I think this is a question to be addressed to a number of other faculty in our department. So I'm going to skip that question.
Great. So next one from Alan Odian. Can the photon detection be stymied by shielding? Can the time of flight scale be thwarted by moderating the neutrons in the warhead, causing diffusion delay?
Can the photon by shielding? Yes, so that's a very good question. Let me just read the second part. Can the time flight scale be thwarted by mere? Yes, absolutely. So theoretically, what the party can do is that they can, for example, the host, what they can do, they can put lots of shielding in the way. They can just kill the signal. That is completely possible. It's not difficult. But that's the whole point. You have to formulate the treaty in a way that says, like, look, we're going to do some measurements, and within an hour, we better achieve some kind of counts. If we don't see those counts, it means you are cheating. You must have put some kind of neutron poisons, or you might have put some kind of a gamma shielding or something like that, and it's not going to fly. So yes, you can put anything you want in the encrypting mask, but within the limits of us having some counts and seeing some resonances, because we know we ought to see resonances for plutonium. If we don't see them, it means you are playing some kind of a hanky-panky with us. By the way, just want to say hi to Alan Garabet Odian. I think we met together back in Armenia in the 80s when Armenia was still part of Soviet Union. But Alan was making a trip to Armenia. I was a 10-year-old kid, and my father was collaborating with Alan. My father happens to be a physicist as well, so we go way back.
So I'm going to go to this one from Patrick Shannon. While the analytical work looks promising, are you also looking, does your work also include methods for falsifying results?
So we have tried. So in our paper, if you look there, you'll see a number of essential examples where we're trying to come up with ways in which the host will try to falsify this. So, for example, these hoax objects, false objects, are an example of essentially what way of essentially doing a unit test on the on this methodology to see if it will be able to reject them or not. It's a fairly limited test. Okay. The number of the objects are infinite. We cannot do it so easily. However, in general, how cryptography works, right? You sort of come up with some cryptographic algorithm or methodology, and then you publish it and you ask for people to red team it, to come up with ways in which to cheat it. And essentially, this is what we're engaged in, right? We come up with some scenarios that we think are the most kind of clear ones that someone could try to use. We show that we're able to catch those. But like with most cryptography, yeah, people, if you can come up with ways to cheat it, please let us know, and we can think about how to fix it.
All right, I think I'm going to call this the last question, if that's okay with you. And I'm going to go to Samuel Major's question here. So related to your comment on being stuck in Cold War thinking, I've heard the analysis that the days of bilateral arms treaties are over and that anything practical now would need to be trilateral, including China. Do you agree? Have you had any reception from Chinese authorities regarding technical collaboration?
I have not had any reception from Chinese authorities, but our colleagues from Princeton have had, and I know that Sig Hecker from CSAC in Stanford has been pretty active talking to the Chinese. I don't know at which stage those conversations are. Let's see, trilateral, bilateral, multilateral. That's a very good question. The reason this is a good question is because one of the reasons that for better or for worse, mostly for worse, the reason that we pulled out from the INF Treaty, Intermediate Nuclear Forces Treaty, was because the Trump administration really wanted to force China into some kind of a similar type of a treaty. So there is definitely thinking in the political establishment and the policy establishment that we need to bring in China into all these treaties. To me, I think it's a little bit of like, if you just look at the number of the warheads, okay, how much Americans, Russians have and how many Chinese warheads there are. I mean, Chinese are a factor of 3 to 4 less, at least less than what we have. As I said, we and the Russians have 90% of the warheads. I feel like, but now there is quite a bit of a discussion that Chinese may be building up their arsenals. Okay. I believe, if I'm not mistaken, the main reason why they do it is not because they're trying to sneak up on us and bomb us or surprise us, but because they're extremely worried by our ballistic missile defense and by the increased precision of our arsenals, which are effectively increased precision means increased numbers of warheads. Okay. If the warhead's precision increases by a factor of 2, that is the same thing as increasing your arsenal by a factor of 4. So I think Chinese are, like most of the time what happens in these scenarios, things when it comes to politics is rather than asking ourselves questions, well, why are Chinese doing what they are doing? Why are Russians doing what they're doing? We sort of like have this very reactive way where like Chinese are increasing the numbers, we need to go hard on them or something like that. And I think some of the reasons why we pulled out from INF Treaty, which I think was very unfortunate, was in part was reflected by that primitive thinking.
Okay, well, we'll jump to this last question from Mark. Global warming is important, but minor versus the risk of MAD. What if
mutually assured destruction? Yeah.
Yep. What if someone had a rational leader or fake data or some software hack? The world should reassess priorities to what's important, including refocusing on nuclear disarmament.
I think we can walk and talk. Okay, I think we can, I don't know, chew and type at the same time. I think the problem of the global warming and COVID-19, earlier question was along these lines as well. They draw from resources that are from a different pot than the resources as a society we need to deal with the risk of mutually assured destruction in case of an intentional or unintentional war. That said, I think the public attention over there, it is the same resource. Public attention is ultimately one resource, and whether public attention focuses on this or that, it seems that, you know, the way it works, it seems to be a zero-sum game, even though it should not be. So I completely agree that global warming, if we simply look in terms of numbers and we look at how many people will die from global warming and how many people will die from an all-out nuclear war, yes, all-out nuclear war will probably send us back to, I don't know, maybe 18th century, 17th century, if not medieval times. It will take us probably 100 or hundreds of years to recover from. So yeah, I think at least in terms of just raising awareness, like in my opinion, nuclear weapons all deserve, the danger of nuclear weapons deserves the same degree of awareness as global warming. I agree with that.
Great. Well, on behalf of the Alumni Association, thank you for tuning in to this MIT Faculty Forum online broadcast. And thank you very much to our speaker, Professor Danagulian, for joining us today. We'll be sure to forward all of the questions that were asked in the Q&A to our speaker, and the chat will actually stay open. Alumni Office chat will staff the chat window for discussion purposes for another 15 minutes or so. This broadcast will be available on the MIT Alumni Association YouTube channel within a week of today's airing. Thank you again for participating.
Thank you for having me. This was exciting. Lots of very interesting questions.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.